Hello. Hello, everyone. I'm Hugh Wang. I'm third year PhD student from Stats Department in UC Berkeley. Bin is my advisor. So I previously worked on dictionary learning. Oh, okay. Previously, I worked on dictionary learning. Basically, our major finding is that sometimes you don't want to find the global minimum. Instead, you want to find a dictionary that is most stable according to certain perturbations, because the objective function you use might only be approximate, but not the accurate objective function. Other than the theoretical project, right now I work on more applied project, we use a non-negative matrix factorization to analyze bioimaging dataset. So I'm very excited to be at this workshop and hope to talk more with you guys. Thank you.
Guess you can hear me. So my name is Eftichios. I work here at the Flatiron Institute at the Center for Computational Mathematics. I spend most of my time working on problems that have to do with image segmentation and signal deconvolutions, and arising problems in fluorescence microscopy in neuroscience. But lately I've been more interested in machine learning problems, and especially problems related to what we just heard on, creating neural networks that respect certain kinds of symmetries and applying to various problems that we work on here at the Flatiron. And thanks to the organizers.
Hi, my name is Ilya, and I am from Oxford, so we should really swap talks. So my own background is in stochastic analysis. So I mostly work on stochastic differential equations and particular rough paths theory and stochastic PDEs. And more recently, I've become interested in data analysis and data science, in that there's some quite powerful theoretical tools from rough paths theory and analysis of stochastic PDEs that have been successful to prove theoretical properties, and we're trying to see how they're able to apply to certain problems in specifically problems in recognizing or learning about time-ordered data. So Terry, I believe, will give a talk about this at some point in time, and I may also be as well, in which case I apologize if I introduce myself. Thank you.
I am Jason Morton from Penn State Mathematics and Statistics. A couple of points of contact for me. I worked on restricted Boltzmann machines and deep learning models, looking at their dimension, looking at their algebraic structure, polyhedral structure. So questions like, if you write down a big model, a lot of parameters, how many effective parameters are there? So what's the dimension of the probability distribution if all the top levels are hidden, which is actually a really hard problem. I've also written a couple papers about statistical physics and quantum information, though I haven't really put these things together except at the level of mathematical tools. Thanks.
Hi, my name is Xiao Li. I'm from the Stat Department at Berkeley. I'm a graduate student working with Bin. So I have a statistical background, and currently I'm working, on the one hand, I'm working on kind of interpretable machine learning, where you want to generate scientific hypotheses from a machine learning model that you trained. And I also work on a couple of applied projects. For one project, we are dealing with this kind of precision medicine data. We have different types of cancer drugs that we want to evaluate which of the drugs will be the most efficient to patients, because these drugs will cost $200 grand a year, so you really want to apply the correct drug to the patients. And we're using machine learning to kind of select the correct drug for the patients based on their full molecular profiles. Yeah. Hope to interact with everybody here, and really enjoyed the talks this morning. Yeah. Thank you.
Hi to everyone. My name is Elena Giusarma. I'm a postdoc here at CCA. I'm a cosmologist, so in particular, my research is focused on neutrino cosmology. So for those who have never heard about neutrinos, neutrinos are electrical neutral particles, and they are everywhere. They weak interact. This means that they can pass through our body every second without interactions. And cosmology is very important because it can give information on those particles. And this occurs because neutrinos affect the different cosmological observables. So my role in the field has been to analyze different cosmological data and performing statistical inference analysis in order to study the properties of neutrinos in our universe. And I'm also interested in applying machine learning tools in cosmology, and in particular in predicting non-standard cosmological simulations, such as simulation with the neutrinos, using deep learning algorithms.
Hi, my name is Gabriela Contardo. I'm a postdoc here at CCA, so Center for Computational Astrophysics. However, I'm not an astrophysicist by background. I have a PhD in machine learning. And basically, I joined here both to work on projects where applied machine learning could be useful, but also to learn more about astrophysics and probably learn more about go further in machine learning, like interesting problem. I work on different type of projects. Mainly, I'm interested in anomaly detections on different type of structured input, like point clouds or time series. I'm also interested in knowledge discovery using machine learning. Sorry for ones who think it's not possible. And I'm also really interested in doing representation learning that are more interpretable or more useful for the astrophysicists I work with. And that's about it. And the last one?
2 minutes, and I can't really talk about myself without showing pretty pictures because I'm doing cosmology and astrostatistics. So I work in Berkeley. I'm affiliated with a bunch of different institutes over there, and my field is really trying to apply machine learning methods for solving some of the problems that show up these days when we try to do cosmology. So the context for this is that we are entering a new era in cosmology. I'm working with this instrument, the LSST. It's essentially a giant robot telescope. It's going to observe the full sky once every 3 days and produce a gigantic amount of data. It's orders of magnitude higher than what we had before in the previous generation of surveys. It's not only a lot of data, it's a lot of very high quality data. So on the left, you have a galaxy as imaged by a current generation survey. And that's what LSST will be able to see. So it sees a lot more stuff, and the images that we have to analyze are a lot more complicated. And what that means for us is that all the methods that we had in the previous years developed to analyze this data are starting to fail one by one, and at all the steps of the cosmological analysis. So I work at different levels. First at the image processing level, where we do a bunch of different things, like for instance, trying to find very rare objects in this giant amount of data. So here it's finding those instances of gravitational lenses that are very interesting to us, but also very rare. In this other example, we're trying to separate out the light of the different galaxies that you see on this image, and that's a problem because they all overlap with some extent with each other. And so for this, we're using a physical model of what the instrument is and what the image is, and some prior information about the morphology of the galaxies. I'm also working at the level of the simulation that we use when we do our cosmological analysis. On the left here is an example of simulated galaxy images that we can produce after learning those models from the data. And on the right, it's an example of using graph neural networks for modeling the properties of galaxies in cosmological simulations, which are expensive to produce, and we can use these methods to scale them up to much higher volumes. And the last level of the cosmological analysis is when you do your inference. And then again, here we have lots of things that we can improve. On the left is an example of a dark matter map. So it's a simulated map of dark matter distribution on the sky. And the way we analyze these maps these days is just by computing a power spectrum, so a 2-point function of these things. And that is leaving out a lot of information. So one question is, how do you build optimal summary statistics that extract the most information about cosmology? And on the right, it's an example of constraining cosmological parameters from those summary statistics that you've extracted. So it's in the realm of likelihood tree inference. So if any of these are things you care about or are interested about, please come talk to me during this week. Thank you.
Thank you, everybody. Now is a great time to thank all the people who just introduced themselves.